This video is to explain the reaction mechanism catalyzed by chymotrypsin. Chymotrypsin belongs to the serine protease family. So if you understand this mechanism, you actually understand the mechanism of several enzymes that catalyze the hydrolysis of peptide bonds. So to begin with, let's draw in the substrate, which is a peptide bond. And there's a special highly reactive, and this of course is part of a polypeptide chain, continues indefinitely, potentially indefinitely in each direction. And there's a highly reactive serine residue with a hydroxyl group that we'll draw in here. That's serine 195. And it's made especially reactive because of constellation of other amino acid residues in close proximity, especially histidine residue here. Histidine 57. And histidine 57 has special properties. It has a pKa that's shifted towards pH 7 by close proximity of aspartate residue that we'll draw in this one time. And that's provides a negative charge, and that's aspartate 102. These three residues, they're called the catalytic triad because they impart chemical reactivity that you wouldn't normally see if these residues were just sort of hanging out in bulk solvent. But in the active site of the enzyme, now you've created a catalytic base close to a potential nucleophile. So the first step of the reaction is for this histidine 57 to act as a base catalyst, and the electrons here will find themselves on the oxygen after movement of the proton from serine 195 to histidine 57. So we'll draw that next. We have our substrate. Nothing's happened to the substrate yet. We're just generating the nucleophile. So now, instead of a hydroxyl group, which is an okay nucleophile, we have this alkoxide ion, serine 195, alkoxide. Much more reactive. And now the proton is sitting here on histidine 57. And just to save time, I'm not going to draw in aspartate 102 anymore. So the next step is nucleophilic attack of this serine 195 alkoxide ion on the electrophilic center at the peptide bond to generate our carbon, now attached to four things. So I'll try to show that we have a change in stereochemistry, or a change in the geometry at this carbon center. It went from a trigonal planar carbon to now a tetrahedral carbon. And this is called the tetrahedral transition state. Oops, I forgot this double bond character here. So, and in this form, the tetrahedral transition state, there are additional interactions between peptide moieties found right here, and they're oriented to interact most favorably to make hydrogen bonds with this oxygen once it acquires this negative charge. So there's a partial positive charge at these peptide moieties. They're provided by residues in the polypeptide chain that are in close proximity to what's going on in the active site. And they're stabilizing this tetrahedral. So there's additional, this is an example of stabilization of the transition state. So transition state stabilization. And that lowers the overall energy barrier separating the substrate from the product. Now, the transition state, even though it's stabilized by these peptide moieties, it's still one of the most unstable species in this whole reaction scheme. So it's going to collapse soon after formation. And there's a certain probability to go back to where we started, and with serine 195 acting as the leaving group, but there's an equal probability of using this amino group as the leaving group. And this is further encouraged by close proximity of a catalytic acid group. So this nitrogen the leaving group can be stabilized by picking up quickly a proton from histidine 57. So histidine 57 is acting as a catalytic base at the very beginning, and then here, as we resolve the tetrahedral transition state, it's acting as a catalytic base. A catalytic acid functional group. And that gives us our final reaction intermediate for this phase of the reaction. We have a free amino group, which is now free to leave the active site, and we have here what's called the acyl enzyme intermediate. And now histidine 57 is back into its deprotonated form, drawn like so, not charged. All right, so we've generated one of the products. This is a new amino terminus for the polypeptide chain. The chain has been broken at this peptide linkage, but we still have the carboxy terminus of this polypeptide chain now covalently attached to the enzyme itself. There's a new covalent bond between the substrate and serine 195 of the enzyme, and this situation is an example of covalent catalysis. All right, and that completes the first phase of the reaction mechanism for chymotrypsin. And in another video, I'll show essentially these same four steps: base catalysis, nucleophilic attack, acid catalysis, stabilization of the transition state of a tetrahedral carbon transition state. It's going to happen again to resolve this acyl enzyme intermediate. And we'll see that in the next video. Cut.